about the fuzzy linear programming in state of minimization. I explained the state of maximization and the expressions and equations of maximization in fuzzy linear programming. So now we are going to familiar with the minimization state. Okay, similar to the maximization, in the first place, we must plot the figure of minimization state and plot of fuzzy membership degree. You have been familiar to this plot previously. Membership function or membership degree for objective function and fx or z equals cx. But our purpose is to minimize the objective function in this section. Okay. There is a parallel line with z in the horizontal axis and in this point that this is considered as the optimum value for objective function, for minimum objective function. And after this point that is called z lower or zl, the membership degree is being decreased. We must write the equation of membership function for minimization state, and the degree, membership degree, is being decreased to receive z up or zu. As you know, the membership function, the membership degree is differed from 0 to 1. For example, in this place, from this point to the point of ZL, the membership degree equals to 1, and after that, gradually, according to this linear equation, the membership degree is being decreased. And we can accept the value for minimum of z, or minimizing the z or objective function, according to membership function, according to the lambda, similar to the maximization model. For example, you can see we have z. Z is more than the, or is greater than the ZL. But we can accept Z a few greater than the ZL, according to lambda, according to the membership degree. And it is better the membership degree approaches to the 1. In total, I should say that our objective in the fuzzy linear program is lambda, and in total it was the models, whether minimization or maximization. Our objective is lambda, so that lambda is maximized. For example, in this figure, we must dwindle the interval between z and zl. We must decrease this distance. And for this purpose, the lambda must be maximized. In the minimization objective function or maximization objective function. Okay. Now I'm going to write the membership function. As you see, for z more than, for z greater than zu, the membership degree equals 0. And for z less than zl or lower bound of z, the membership degree equals 1. But for z in the interval of the z lower and z upper, this distance, this interval, you can see we can obtain the equation or fraction of membership function. Okay, by dividing zu minus z or cx. Z is objective function and this is variable, but zu and zl are constant value obtained by solving the model or CRISP model. By dividing zu minus z by zu minus zl. Also, this equation, this fraction, is called lambda, so that we must maximize lambda again. Okay, by dividing zu, this distance, this interval, zu minus z, dividing by zu minus zl, we can calculate dividing this value, lambda or mu, by this value, mean 1. This value equals 1. Okay, so we can rewrite the formulation of okay. As you see, we can rewrite this formulation again. Zu minus z divided by Zu minus Zl is greater than lambda, so that the lambda is maximized in the certain or converted modeling after converting the fuzzy model to the certain model. So Zu minus z is greater than lambda multiplied Zu minus Zl, and we can rewrite this formulation to this structure: lambda Zu minus Zl plus z is less than Zu. This is the first formulation or private formulation for just objective function. And I want to present or show the structure of general formulation. If similar to the maximization model, if we assume that the general notation for this difference, for this deviation, for example, Zu minus Zl, we can assume that this is notated by P. P is called the allowable deviation or tolerance for considering the objective value more than the optimum value in the minimization model. Okay, so this can be multiplied. This can multiply on the lambda plus Cx instead of z is less than Zu minus Zl plus Zl. As you see, the conclusion of this expression equals to the Zu. And what is the Zu minus Zl? This is called P. P plus the allowable difference or deviation or tolerance plus Za. And what is the Zl? Zl is same as the value is placed on the right side. Okay, right side of the equation or inequality. In the format of general format. Okay, and I rewrite this equation: P lambda plus Cx is less than P plus D. In the general, we have this inequality or constraint. The maximum or minimum is another constraint that we have written this to the structure of maximum or minimum. But in this section, we are going to discuss about the minimum. A minimum Z equals Cx. So it means that Cx is less than Z. Okay. Therefore, we can rewrite the minimum. If we assume minimum is equivalent, Cx is less than Z, L, conclusively, we can rewrite this equation or this inequality, lambda p. Let me consider the p and lambda p. Lambda multiply p is added to the left hand side, and p is added to the right hand side. As you see, lambda p plus Cx, okay, is less than p plus ZL. And this is another way to obtain the formulation. This formula is considered for constraints. This formula is considered for minimum objective function, and also this formula is considered for minimum objective function. All formulas are equations or inequality are similar to each other, and these are different from each. These are not different from each other. As you see, ZL plus P similar to this part, ZU minus ZL plus ZL. And in this part, I'm going to categorize the fuzzy models, fuzzy linear programming models in the literature. The first class is related to the approximate or uncertain about the maximum objective function or minimum objective function. Two classes related to the uncertainty, the constraints. And three is uncertainty about the coefficients. For example, A, technical coefficients, C, the objective function coefficients, and B, the numbers that are located on the right hand side in the inequality or constraints. Okay, now we are going to give you 4 examples about fuzzy C, fuzzy constraints, and maximum minimum, fuzzy B and fuzzy A and B simultaneously. Okay. In the first place, we are going to have example about the formulation of the maximum or minimum and constraints in figure of fuzzy, and then I will give you an example. Total, you have this format: maximum z equals cx subjected to ax is less than b. In the first place, we can convert this structure to the constraints totally. We can convert this structure to the constraints. In the first place, I must convert the objective function to the constraint. Cx is greater than z, format of fuzzy logic. Okay, and after that we have this form, this constraint. Then we can convert it to this by multiplying negative. And then we can show this vector negative c and a is less than this vector, negative z and b practice. Excuse me. Okay. In total, we must rewrite the structure of fuzzy linear programming, convert it to the certain or crisp linear programming. As I said before, our purpose is to maximize lambda. So our objective function is lambda, so that it must be maximized, subjected to the okay. After that, we called this vector b and we call this vector D. Bx is less than D. Okay, Bx is less than D, but applying tolerance. Tolerance is determined by lambda. Lambda must be maximized, and lambda p, similar to previous slide, lambda p is added to the left hand side and p is added to the right hand side. Lambda p plus to the bx and p is added or plus to the d, and x and lambda are greater than 0. This is the crisp converted linear programming. When you are solving this linear programming, you are considering the fuzzy conditions in the linear programming model. Now I will give you an example for this model. Okay, in company, our objective is to minimize costs and costs of transportation and other parts. Minimum z equals x1 x2 x3 and x4, subjected to the first constraint 0.84 x1 plus 1.44 x2 plus 2.16 x3 plus 2.4 x4 is greater than 170, and another constraint 16 x1 16 x2 16 x3 16 x4 are greater than 1300, and also the last constraint x1 is greater than 6. Okay. x2, x3 and x4 are non-negative decision variables. After solving this model, this deterministic model, the solution is shown following expression: x1 star equals 6, x2 star equals 16.29, x3 optimum value equals 0, and optimum value of x4 equals 58.96, and the minimum cost equals 3 million. Okay. So the management system want to consider a few deviation for the objective function and the constraints. For example, the management system consider these deviations. For example, they consider that objective function is considered for ZL or D. D in this example equals to the ZL, as you see, ZL and D. Okay, ZL and D are similar to each other. So the lower bound for Z is considered, for example, 3,700,000. But we could consider equals to the optimum value. But in this example, the designer have considered this value for the lower of Z. And P P1 is considered equals to 500,000. And about the constraints. First constraints, D2 is 170, and tolerance is considered to be 10, according to the management system and their determination. Constraint or second constraint, as you see, equals to the 1,300. But allowable deviation is considered to be 100. And the third constraint, D equals 6, and P also equals 6. Okay. As you know, the equation for the maximization is P lambda minus Cx is less than P minus Z u. But for minimization, The equation is P lambda plus Cx is less than P plus ZL. Okay? And now we can write all inequality or all constraints. For example, for the first constraint, we can follow from this equation Bx plus P lambda is less than P plus D. Okay, for the first, plus 48 100 x3 plus 49 100 x4 plus P lambda, P 500,000 lambda less than D plus P. In on the right hand side, we must add this number and this number. Okay. And for another constraints, we can write these inequalities similar to the first objective function or first constraint. In another section, I will explain about the other structure, fuzzy structure of linear programming in the literature.